In today's lesson, we want to talk about the product rule. Consider the following function. To take the derivative of this just using the power rule, I would have to expand out every single one of these terms. Through multiplication here, we would have to multiply 9 terms together when we're all done. The computations can be fairly messy, fairly tedious, and take a long time here. So is there a better method? And yes, there is a better method. The more effective method is called the product rule. And that's what we're going to look at today is what is the product rule and how do you prove it? So what the product rule says is that if you have two differentiable functions, in this case f and g, then the product of those is itself a function, and that function has a derivative defined to be the following. Fg prime is equal to the first times the derivative of the second plus the second times the derivative of the first. What this means is if you view this as your first function, your f, and g as your second function, then its derivative will be the first function, which is f, times the derivative of your second function, which is g prime, plus the second function times the derivative of the first function f prime. Let's take a look at a proof to see why this is true. Recall that fg acting on x, by definition, is f at x times g at x, and fg acting on x plus h is f at x plus h times g at x plus h. Therefore, let's apply this to our derivative using first principles. Using our definition of first principles, fg prime by definition would be the limit as h goes to 0 of f at x plus h times g at x plus h minus f at x times g at x, the entire expression divided by h. Notice now I've rewritten my expression, but I've added in an f at x plus h g at x and subtracted that same term out of the expression. So effectively I've just added 0, but I've done this for a particular reason. I'm now going to group together select terms so that we can get our proof of the product rule. By grouping the following terms together and separating, we get, notice here now I have a common factor of f at x plus h in the first term, and in the second term I have a common factor of g at x, which I'm going to factor out. Doing so, we get, notice when I apply the limit, I can apply the limit to each function individually. That's one of the properties of limit. So here the limit as h goes to 0, I can take the limit of f at x plus h, and then take the limit of this expression here individually. Likewise, the limit can be applied to each of these terms. So let's do that now. Applying our limit to each expression, you'll see here that the limit as h goes to 0 of f at x plus h will just be f at x. The limit as h goes to 0 of this expression is exactly g prime at x. The limit as h goes to 0 of g at x is just g at x, right? There is no h in my function here. Therefore, the limit has no effect on the function g at x. And likewise, the limit as h goes to 0 of this expression will be f prime at x. Writing this down, we get f at x times g prime at x plus g at x times f prime at x, which is exactly our product rule. Let's take a look at some examples applying the product rule. Looking at our first example here, we're going to view this function as our f at x and view this function as our g at x. Doing that, we want to take our derivative, so we'll say dy dx is going to be equal to the first times derivative of the second plus the second times the derivative of the first. In which case here, dy dx is going to equal the first times the derivative of the second is going to be 6x minus 1 plus the second times the derivative of the first is going to be 6x squared. Keep in mind here, when you take the derivative of 3x squared minus x, you drop down the 2, in which case you get 6x. For this one here, you have x to the power of 1. If you have x to the power of 1, you drop down the 1, so it becomes 1 times x times 1 minus 1, which is 1 times x to the 0, which is 1. Also, when you take the derivative of 2x cubed plus 5, the derivative of your constant value is 0. Expanding everything out here and collecting like terms, we get 30x to the 4th minus 8x cubed plus 30x minus 5. All right, let's take a look at another. So for this question here, we're going to view the first function as our f at x and the second function here as our g at x. Again, it doesn't actually matter. You can switch the order if you want, but obviously it's a lot easier to follow your formula that we've developed. So we have here first times the derivative of the second plus the second times the derivative of the first. Collecting like terms and simplifying, we end up getting 4y minus 7/3 y to the 4/3 minus 6y squared plus 10/3 y to the 7/3. All right, let's take a look at another. So for this question here, we want to find the slope of the tangent to the curve, and this is our function we want to look at the curve of at the point 1. So essentially we want the slope at 1 of this function. So let's go ahead and take our derivative. Now y prime is going to be the first times the derivative of the second will be 9x squared plus 1 plus the second times the derivative of the first will be 1 minus 4x. Now in this situation here, we want to find the derivative at 1. So we're going to go ahead and substitute a 1 into here, in which case we get y prime is, this will be 0 times 10 plus 3 times negative 3, and we get the slope of the tangent to this curve at 1 is negative 9. Let's take a look at another. So for this question here, they want you to find the equation this time of the tangent line to this curve at 1, 5. Well, same idea here. We need to find the slope at the point 1, 5, in which case here we get dy dx is going to be the first times the derivative of the second will be 0 plus 1/2 x to the minus 1/2 plus 3 plus the second function times the derivative of the first will be 0 minus 1/2 x to the minus 1/2. So now we evaluate this derivative when x is 1, and we get 2 minus root 1 is 1. Here we end up getting, I want to express this here, this ends up being 1 to the power of negative 1/2 is just 1. This ends up being 1/2 plus 3. For my next sequence here, this becomes 1 plus 1 plus 3, which is just 5. And lastly, this becomes negative 1/2 left over with. And we end up getting here 1/2 plus 3 minus 5/2, which ends up being here negative 4/2 plus 3, which is negative 2 plus 3, which is 1. So therefore, the slope at that point is exactly equal to 1. We need to find the equation. Well, the slope is 1, and the point they gave us was 1, 5. So the equation becomes y equals x plus b. Subbing in our point here, we end up getting b is 4. So the tangent equation is y equals x plus 4. This is the tangent to the curve at the point 1, 5. Okay, that concludes today's lesson on the product rule. Please review these examples, try some on your own, and keep in mind that you're calculating the first times the derivative of the second plus the second times the derivative of the first. Thank you.